Alright, we're going to start Chapter 2 and with Inductive Reasoning. So first off, we're going to look at some patterns. So we're going to try to find the next item in the sequence. So you have months of December, November, October. So what comes next? Well, September. 3, 6, 9, 12. Next comes 15. Arrows pointing to the left, pointing up, pointing to the right. Next would be pointing down. Now this one's a little bit different. It might take you a little bit longer to figure this one out. Have numbers 1, 1, 2, 3, 5, and 8. And so see if you can figure out what the next number in the sequence would be. Well, it's going to be 13. The way we get 13 is that if you notice 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and 5 plus 8 is 13. And this sequence is actually famous enough, it has a name. It's called the Fibonacci sequence. And not only is it found in math, and in fact, as the higher you go into math, the more kind of interesting details you can find out about this sequence. But it's also found a lot in some of the life sciences as far as like reproductive cycles and like flower petals, things like that. It comes into play a lot all over the place. So what we've been just doing is called inductive reasoning, which is reasoning that a rule or statement is true because specific cases are true. Essentially, we saw some particular items in a sequence, and so we reasoned that we could tell what the next item in the sequence would be. And in fact, we were making what's called a conjecture. So a conjecture is a statement believed true based on inductive reasoning. We essentially were saying that, well, okay, it looks like we're going doing the months backwards, so that's our conjecture, so the next item would be September, that type of thing. So let's say we've got a conjecture here that says the product of an odd and an even number is blank. And so we want to know, okay, is it going to be odd, even? We don't know what. So let's look at some specific cases. So let's consider, some products of odd and even numbers. So if you take 2 times 3, you get 6. 4 times 7, you get 28. 2 times 5, you get 10. It looks like all of these are going to be even numbers. So our conjecture is that the product of an odd and an even number is going to be even. Now, if a conjecture is going to be true, it has to be true for every single case. It can't just be true some of the time. If you can find just one example for which the conjecture is false, then that will disprove it. For example, let's say that we'd come up with some sort of weird case where we had an odd and an even number, that when we multiplied them, we suddenly got an odd number. Well, that would disprove our conjecture. Even if all the other examples we came up with were even, if we had just one example that was odd, that would disprove it. Okay? So this example that we come up with, if we come up with some other an example that makes something false, is called a counterexample. Okay? It's essentially what makes a conjecture false. Now, you've been actually probably been coming up with counterexamples for a long time. You just didn't realize you were doing it. Like, for example, let's say that your parents are telling you that all of those kids over there are bad news or something, and you can say, well, so and so over there, he's a really good kid. He's doing this, he's doing this. He's not one of those. He's not a bad kid. Okay, that's a counterexample. Or again, I mean, whenever your parents are telling you that something is always true, if you come up with some reason why, well, no, that's not always true. That's a counterexample. Here's another one. Let's say, okay, find a counterexample to the conjecture that all students who take geometry are 10th graders. Well, if you're one of my students, you are yourself a counterexample because you are not a 10th grader. So the steps for using inductive reasoning. The first step, okay, you're going to look for a pattern. Then you want to make a conjecture, make a some sort of plan here. What exactly is going on? Then you either want to prove the conjecture is true, or find a counterexample to disprove it and then start over again. So, for example here, I'm telling you that each of these conjectures is false, and so we're going to find a counterexample that shows why they're false. So if I've got a conjecture that the product of any two numbers is greater than the numbers themselves. Now, you can see where someone might make this conjecture because they look at, okay, 3 times 4 is 12, 5 times 6 is 30. Okay, you're always getting these bigger and bigger numbers. And so for a counterexample, you want to come up with some example where this is not true. You multiply two numbers together and you get a smaller number. Well, one example might be, say, 0 times some number. 0 times anything is 0, which is definitely not greater than the numbers themselves. Another example might be, like 1 times something, because again, you get a number that's not greater than the numbers themselves. We can also pull in negative numbers here. So negative 1 times 5, for example, is negative 5, which is definitely not bigger than negative 1 or 5. Okay, another conjecture is that two complementary angles are not congruent. Okay, so someone looks here and they says, okay, I've got these, again, complementary angles add up to 90. And so someone looks and says, well, okay, I've got this, this 40-degree angle and this 50-degree angle. There's a 60-degree angle and a 30-degree angle. So, all these angles are going to be different that add up to 90 degrees. And so your counterexample, let's see if you can think of one right now. Again, so our counterexample has to be two complementary angles that are congruent. That's our counterexample. So that would be 45 and 45. Okay? When you're looking for counterexamples, you're looking to have the first part of the statement to be true, so we want two complementary angles. And we want the last part of the statement to be false, so we want these to be congruent. Now, inductive reasoning is also useful because sometimes we can solve a problem that we're not quite sure it has a pattern, but we can start to kind of play with it and see that one develops. So, for example, let's say I have a problem that says find the sum of the first 20 odd numbers. Now, I could sit down and just do that. I could say, okay, 1 plus 3 plus 5 plus 7, and I could add all those together. But what if they didn't say, well, okay, not the first, I want the first 100 odd numbers. Well, that starts to get really kind of messy. So if we could find a pattern, we could save ourselves a whole bunch of work. So we'll just start off with just one odd number. Okay, well, the first odd number is 1. Well, the sum of 1 is just 1. Okay, the first two odd numbers is 1 plus 3, which is going to be 4. The first three odd numbers is going to be 1 plus 3 plus 5. Well, that gets me 9. Then I do 1 plus 3 plus 5 plus 7, and I get 16. And I don't know about y'all, but I'm starting to see a pattern here. So see if you can figure out what this pattern that we've got going on. What do you notice about these numbers 1, 4, 9, and 16? I'm hoping that you'll notice that, well, 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, and 16 is 4 squared. So that leads me to believe that the first 20 odd numbers then is going to be 20 squared, which is 400. Or I could then take any number of odd numbers, any number of the first odd numbers, whether it's 100 or 1,000 or however many I wanted, and I could figure out what that sum was based on this pattern. Another type of inductive reasoning is finding what's called the nth term. And we call it the nth term because we're looking at basically using algebra to produce what's called a function. And when we're dealing with sequences, we usually don't use x, we use the letter n. And so we want the nth term, we want the term that kind of defines the pattern. So let's say I've got this sequence here. And my first term is going to be negative 3. Then I have negative 2, negative 1, 0, 1. And so then it goes 2, 3, 4. But now I want the 20th term. And I don't really want to sit there and just be counting on my fingers how far that's going to be. So what I notice here is that, well, the difference between the place in the series, or what's going to be my n, and the number itself, the number is 4 less than whatever the place is. For example, 5 minus 4 is going to give me 1. 4 minus 4 gives me 0. 8 minus 4 gives me 4. So my pattern is going to be n minus 4. So the 20th term would be 20 minus 4, which is 16. Okay, so let's try that with a little bit harder pattern. This time I've got bigger numbers, but we're going to use kind of the same idea. So it starts off with 32, then it goes 39, 46, 53, 60. Okay, what is it going up by each time? Okay, it's going up by 7. So the 6th term would be 67, then comes 74, then comes 81. Okay, but now how do I find this 20th term? Well, the way that you do this, there's 2 steps to this. If you've got a pattern where the difference is the same, so these are all going up by 7. So it's like they're all going up by 7, all going down by 2, whatever the pattern is. Okay, that's what's going to go in front of your n. So since it's going up by 7, what's going to go in front of my n is 7n. Then I'm going to take whatever the number before my first term would be. Okay, so if I'm starting off with 32, the term before that would be 32 minus 7, which would be 25. So that's going to be my starting value. So my rule, my function, is going to be 7n plus 25. So now that I know my rule, I can plug in 20 for n, and I get 7 times 20 is 140. 140 plus 25 would be 165. Okay? So again, make sure that you've gotten your questions written for this. If you haven't already done so, go back to your previous objectives. Any that you don't have summaries written, go ahead and write those summaries. Kind of get all the first chapter's worth of stuff kind of cleaned up and put together, so that way you have it handy when you have that handy available to you for when we have our semester exam later in the semester. So, thanks.